Welcome. My name is Jesse Fosheim, and today I will be discussing efforts at the Colorado School of Mines investigating effective heat transfer in narrow-channel fluidized beds for primary heat exchangers and particle thermal energy storage systems, with a particular focus on coupling concentrated solar power to supercritical CO2 power cycles. Solar-driven SCO2 power cycles are being pursued for next-generation concentrated solar power plants. Compared to conventional steam Rankine cycles, SCO2 power cycles provide higher efficiencies with decreased capital costs and reduced water usage. Particle-based thermal energy storage offers arguably the most feasible near-term solution for linking CSP to high-efficiency SCO2 power cycles that operate at temperatures in excess of 700 C. Engineered alumina-silica particles are inexpensive, mechanically robust, chemically inert and non-corrosive, and offer a wide range of operating temperatures. On this slide, I show a schematic of a solar-driven SCO2 power plant with particle-based thermal energy storage. On the left, solar heat is stored in the particles as they pass to a particle receiver irradiated by concentrated sunlight at fluxes up to 1,000 suns. The heated particles feed the hot side of a particle SCO2 heat exchanger, where the solar heat captured in the particles is transferred to the SCO2 to drive a Brayton power cycle like that shown on the right. The cooled particles are then collected and recycled back to the receiver. Of the subsystems necessary for implementing particle-based thermal energy storage for CSP, the particle receiver has received the most attention, with some prominent examples shown to the right. On the other hand, the particle SCO2 heat exchanger, which similarly represents one of the most important components of the thermal energy storage system, has not received the same level of attention, and therefore comprises one of the primary risks and uncertainties for scale-up and commercial implementation of particle-based thermal energy storage. Current designs for particle SCO2 heat exchangers rely on moving packed beds where the particles transfer heat by sliding contact with the confining walls. However, while the SCO2 flow provides effective heat transfer, with effective convection coefficients in excess of 2,000 watts per meter squared Kelvin, the heat transfer coefficient on the particle side is fundamentally limited by the low effective thermal conductivity of the bed, resulting in effective particle wall heat transfer coefficients generally less than 3,000 watts per meter squared Kelvin. This approach therefore requires large heat exchangers with short conduction length scales on the order of a few millimeters, creating significant operating challenges and making it difficult for these designs to meet cost targets for next-generation CSP plants. Prior works at mines demonstrated that significantly higher heat transfer coefficients, in excess of 1,000 watts per meter squared Kelvin, can be achieved in small narrow-channel fluidized beds, suggesting that this approach could enable small, cost-effective heat exchangers in particle-based thermal energy storage. Towards that goal, we established a new larger-scale narrow-channel fluidized bed experimental facility. The facility is shown here configured for low-temperature operation with flow visualization. The bed depth is 18 millimeters, multiple times larger than those required for moving packed beds. During operation, particles are gravity-fed from a heated hopper into the top of the channel and are fluidized by air injected through a tube with an array of 200-micron holes. This facility is modular with interchangeable walls. Heating is provided by an array of quartz lamps. The irradiated wall is instrumented with thermocouples embedded in the internal and external surfaces. For high temperature tests, the window is replaced with another instrumented wall, or both walls can be replaced with air-cooled microchannel plates to simulate the forced cooling that would be provided by SCO2. Thermocouples to the side of the channel measure bulk bed temperatures, and differential pressure transducers provide pressure drop measurements across various height locations of the bed. To date, tests have been performed using Carbo AccuCast ID50 particles with a mean diameter of 260 micron at 100 to 400 C and superficial gas velocities up to 0.55 meters per second. These videos illustrate operation at two different superficial gas velocities. With the left video is for gas velocities of 0.18 meters per second, about 125% of the minimum fluidization velocity, and the right with 0.28 meters per second, approximately twice the minimum fluidization velocity. Particles enter in a steady stream at the top and are spread quickly to fill the full width of the channel before traversing steadily downward to the bottom of the bed. The fluidizing gas injected at the bottom coalesces as it rises through the bed, with larger bubbles and more vigorous fluidization apparent with higher gas velocities. These figures illustrate representative transient data. The left figure shows temperatures measured at the same location on the external and internal surface of the heated wall, and bulk bed temperatures measured above and below the wall measurements. The red line in the middle is the instantaneous local heat transfer coefficient based on the measured conduction through the wall and the temperature difference between the internal wall surface and the fluidized bed. The right figure displays particle volume fractions along 4 sections of the bed height based on pressure drop measurements. These data demonstrate that particle volume fraction remains quite uniform along the height of the bed and provides useful information for flow control when bed visualization is not available. This figure demonstrates average particle volume fraction as a function of temperature and a dimensionless excess gas velocity denoted as U hat. As expected, we observe decreasing particle volume fraction with increasing temperature and gas velocity. Nonetheless, over the full operating range, we maintain relatively high particle volume fractions, which we expect to be beneficial for achieving effective heat transfer. At a U hat of 0, which represents minimum fluidization, the particle volume fraction is approximately 0.57, which matches the packing density of the particles, and at a U hat of 100, a velocity approximately 5 times the minimum fluidization velocity, the particle volume fraction is 0.45. At projected desired flow rates for this geometry of around 9 grams per second, these particle volume fractions correspond to average particle residence times between 75 and 100 seconds. This figure presents average heat transfer coefficients for the same set of tests. We see that heat transfer increases with increased temperature due to the corresponding increase in the thermal conductivity of the gas, and at higher temperatures the increased contribution of radiative heat transfer. Interestingly, we observe a peak in heat transfer at intermediate gas flow rates. In fact, this behavior may be beneficial for our application, as increasing gas velocities increase the parasitic loads for pumping and heating the gas. At temperatures and particle flow rates expected for particle SCO2 heat exchangers, this maxima corresponds to quite low gas utilization with particle-to-gas flow rate ratios of less than 2%. From these data, we construct a new heat transfer coefficient. We quantify the radiative component treating the particles in the wall as gray surfaces with relative U factors of 1. The particle convective component is fit with a Nusselt number correlation that follows the general form used by Molaris. The Nusselt number is modified by 1 plus the inverse of a two-phase Prandtl number and is fit as a function of U hat and the laminar Archimedes number. Various functional forms are considered and fit to the data using a nonlinear least squares fit solver. The resulting correlation is shown at the top. The functionality with respect to the laminar Archimedes number is a simple power law relationship, and the U hat functionality follows a general gamma distribution. The left figure shows our correlation plotted alongside the experimental data. In the right figure, the predicted heat transfer coefficient is plotted with respect to the measured heat transfer data at the same condition. The solid black line denotes the correlation perfectly matching the measured data, and the red dashed line denotes deviation of plus or minus 10%. While the presented correlation is preliminary and is being updated as we collect additional data, it is encouraging that the current approach captures all experimental data to date within plus or minus 10%. We extend the use of this correlation to predict tentatively heat transfer coefficients at higher temperatures and varying particle sizes. Here we show a contour plot of heat transfer coefficient as a function of bed temperature on the left and particle diameter on the bottom. While these projections are provisional, they are nonetheless promising. With currently available particles like 260 micron AccuCast ID50, like those used in these experiments, we project heat transfer coefficients above 1000 watts per meter squared Kelvin at temperatures above 600 C. Moreover, decreasing particle size is expected to provide significant gains in heat transfer, with heat transfer coefficients increasing with 160 micron particles by almost 40%. These data are being used to inform the design of a prototype 40 kilowatt particle SCO2 heat exchanger that is to be fabricated and tested at Sandia's SCO2 flow loop. Here I show schematics of the general heat exchanger design. The heat exchanger will comprise a bank of narrow-channel fluidized beds separated by diffusion-bonded plates with microchannels for single-pass counterflows of SCO2. If you are interested in this work, please attend the presentation by my colleague Xavier Hernandez to learn more about the design and modeling efforts. In conclusion, we have established a new larger-scale test facility for investigating the impact of bed operation and particle properties on heat transfer and fluidization in a narrow-channel fluidized bed. To date, we have performed experiments with Carbo AccuCast ID50 at temperatures between 100 and 400 C and superficial gas velocities up to 0.55 meters per second. We have demonstrated particle-to-wall heat transfer coefficient up to 750 watts per meter squared Kelvin with particle volume fractions greater than 45%. We developed a new heat transfer correlation that matches data within plus or minus 10%. Using the correlation, we projected particle wall heat transfer coefficients in excess of 1000 watts per meter squared Kelvin at conditions relevant for particle SCO2 heat exchangers. Future work includes additional testing with alternative particles and at temperatures of 600 to 700 C, and using these data and the revised heat transfer correlation to inform the design, fabrication, and testing of a prototype heat exchanger to demonstrate this technology at scales relevant for CSP plants and other high-temperature thermal energy storage applications. Finally, I would like to acknowledge the organizations and individuals listed here for their support of this work.